So let's start the morning session. We have an exciting list of speakers. Frank Pollmann.
Okay, thanks, Joel. And thanks to the organizers for giving me the opportunity to give some lectures here. And hope it will be not too bad to hear me in 3 consecutive lectures. So in previous lectures, basically everything or most of the kind of topological concepts could be understood in terms of a band theory, or in terms of non-interacting electrons. And in today's lecture, I want to discuss the case of interactions, right? So if we want to discuss what happens if we add interactions to the systems. And let me also stress that please ask questions. So whenever something is not clear, please ask. So I'm happy to give some extra explanations on the board. So before starting talking about how to simulate these systems, I want to give a brief motivation for why I think this is important. And there are different setups or like different kind of ideas where like how interactions will be considered. The first one is, and this is quite similar to ideas that you heard before, we could start, say, from a tight binding model on a lattice, like say that we take a honeycomb lattice with some hopping between nearest neighbors and potentially next nearest neighbors. We could have some phase vectors in these hoppings, giving us eventually the Haldane model. And for this Haldane model, we can then get the band structure, which would be this one here. And then we know that we can derive topological invariance for the system. For example, we can calculate the Chern number for each band. And then we know that if we just completely fill the lowest band, then we have a Chern insulator. And this is very similar to the physics found in the quantum Hall effect and the like. So all this is at a level where the interactions are completely neglected. And one question we then might ask is like, what happens if we actually go away from this non-interacting limit? What if we, for example, turn on some nearest neighbor interaction? Right? A question that we could ask, like, to which extent are these topological invariants that we introduced before actually still well defined? And moreover, if we just make these interactions strong enough, eventually we'll expect that the phase becomes unstable and that there would be a phase transition to another potentially symmetry breaking phase. And again, we might be interested in understanding what kind of phase transition does actually occur. So this is one case where we might want to study the stability of the non-interacting topological phases that we have identified before. But in fact, in the presence of interaction, much more, I think, exciting things can happen. So for example, we could think of a scenario where the non-interacting system is not kind of topological in a way. So just staying with this example, we could think that, well, we just partially fill the lowest band. Right? So we just have a partially filled band, and then at the non-interacting limit, what we have is clearly a metallic state. But then we can say that, well, let us now take like a start from a metallic state and turn on some interactions. And in these cases, it turns out that then quite some interesting sort of collective phenomena can yield to some completely different class of topological phases. In this example, if we just partially fill the lowest band of this Haldane model, for example, due to interactions, a gap can open and so-called fractional quantum Hall states can be formed. And these fractional quantum Hall states are topological in the sense that they have kind of fractionalized excitations, and they are kind of classified by sort of interacting topological invariants. Something that I'm going to touch up on a little bit towards the end of my lecture. But we can also take models where there's no kind of connection to non-interacting models. We could, for example, take some simple spin Hamiltonian. So, for example, here the Heisenberg Hamiltonian on a specific lattice. So, for example, we can the Heisenberg lattice on the Heisenberg model on certain kind of frustrated lattices, for example, the Kagome lattice, and then ask if we take this Hamiltonian, what is the ground state? Like, what are the properties of the ground state? And clearly, we know that if we take this Hamiltonian and put it on a simple, say, square lattice, In that case, the ground state will be antiferromagnet, so it will spontaneously break symmetry. But if we kind of choose specific lattice that frustrate or basically make this specific ordering pattern impossible, there's a hope that systems might form some more exotic and potentially topological phases of matter. And again, in order to find these or to understand these kind of phases, we actually need to study a rather complicated kind of quantum many-body problem. So this is what I want to focus this lecture on, or basically this series of lectures on. Namely, I want to first discuss how can we actually efficiently find it, because as I explain in a moment, studying this many-body problem is extremely difficult. And after having discussed some ways how we can simulate these systems, I want to discuss how we can actually use the results that we get to extract sort of some many-body topological invariants that will allow us to characterize these phases. And if I have time at the end, I actually want to discuss a little bit how we can actually go away from the ground state, but just look at dynamical signatures of these phases, which then gives us a chance to compare to experiments. Good. Yeah, with this, I want to now point out the main complication that we are running into. Because in order to understand the kind of emergent or collective phenomena of these many-body problems, we actually have to work in the many-body Hilbert space. Right? So let us now, for concreteness, think of a simple lattice system where on each side we have certain degrees of freedom. And again, to be very concrete, we could think of a spin system, right? Like this Heisenberg model that I talked about before. And in that case, each of the sides can be in a local spin state that could be either up or down. Right? In that case, this variable Jn would be either kind of 0 or 1 or up and down. Right? So in that case, we have a two-dimensional local Hilbert space. Right? If we just want to diagonalize the Hamiltonian for a single side, all we have to do is to diagonalize a 2x2 matrix. If, however, we are looking at a larger lattice, and this is what we ultimately want to do, we actually find that the size of this many-body Hilbert space, or like the number of basis states in this many-body Hilbert space, is increasing exponentially with the system size. Right? So the dimension of this Hilbert space is growing as d to the power of L, or L is the number of sides in the lattice. Then if we have just created the basis for this complete Hilbert space, we can express every state in this space. But now we see quite immediately the complications we're running into. Because the size of the matrix, we're very quickly running into a hard wall when it comes to computational resources. So even with a moderately large computer, for a spin 1/2 system, we can, for a full diagonalization, reach up to roughly 20 or so sites. So this means that if we just construct the full many-body matrix, but there are some more efficient methods so that we don't actually have to store all elements of the matrix, but we just store those non-zero elements. So we just make use of certain structures of this Hamiltonian, and then we can go up to roughly 30 or so sites. So basically, if we compare the complexity of this problem to non-interacting problems, it's incredibly much more difficult, right? Because a lot about topological insulators or Chern insulators or wild semimetals can be learned just by diagonalizing a 2x2 or 4x4 matrix. Here, the matrices that we would have to diagonalize to understand the problem is exponentially large in the system size. Good, and this is basically now setting the stage for the 3 lectures that I want to give. In the first lecture, I will take some time and discuss certain properties of these many-body wave functions. So in particular, what I want to show is that the ground states that we might be interested in, right, ground states of our Hamiltonians, they will actually have some rather special entanglement properties, which will then allow us to derive what we call an efficient description. Right? So the magic that I want to show here is that while storing the full wave function would store, would basically need all storage, like it goes beyond the storage that we possibly have. But using some tricks, or like using the so-called matrix product states, we can actually compress the information to actually to a size that we can handle it on a laptop. And once we know these techniques, I actually want to show how from this setup we can actually extract topological invariance. So there, just give some ideas about the different topological invariants that we have for a number of interacting systems, and then show how we can obtain those from matrix product states representations. And again, if time permits, in the last part, I want to discuss a little bit about the dynamics of topological phases. Good. So with this, I want to start talking a little bit about this concept of entanglement. Let us now assume, like similar to the setup before, that we have now a system of L sites. And for simplicity, I want to think for the first part just of a one-dimensional system. Right? Just we can think of a one-dimensional chain of length L. And the generic many-body wave function can be expressed in terms of these basis states, which are just product states of the local states. And here I want to introduce a concept of the so-called Schmidt decomposition. And this will be quite essential throughout this lecture. So I want to take a little bit of time to explain this idea. So what we are, well, as I pointed out, so we just have now our one-dimensional spin chain, as shown here by these black dots. So what we are doing now is we are just forming a bipartition of this spin chain. So what it means is we just kind of choose a bond, and we just draw this dashed line, and we just separate the degrees of freedom into anything that's left of our cut and everything that's right of our cut. Right? So we have subsystem A and subsystem B. So this is now a bipartition of our system into two parts. So clearly, we can now express any wave function that lives on our entire system, like on our entire chain, in terms of some basis states IA. These basis states IA, they are forming on some orthogonal basis for the left part, and some basis states JB forming an orthogonal basis for the right part. Right? Just for the concrete spin system, these I could be, for example, all SZ eigenstates on this side, right? Like up, 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 down, and so on. Now, we have here this coefficient matrix, and this coefficient matrix is now just giving us exactly the state that we are interested in. But what we can do now is we can actually perform a singular value decomposition of our coefficient matrix, and writing it as a product of a unitary times a diagonal times another unitary matrix. And these unitaries give us a basis transformation from this local basis, or from this basis that we have chosen here, to a new basis in which this matrix Cij is diagonal. Right? So what we get from that is that we actually then have an expansion of our, like a representation of our state as a superposition of product states between the left part and the right part. And the states alpha A and alpha B, they're so-called Schmidt states, and they are forming by themselves, again, an orthogonal basis for the left part and the right part of the system. There are some very simple limits that we can think of. So think of a product state. Let's say that the state that we have is a simple product state where we just have, for example, a simple ferromagnetic wave function. In the case of this, in case of this very simple product state wave function, this Schmidt decomposition would only have a single non-zero Schmidt value, which would be 1. And then this alpha state, the corresponding alpha state, would be the all-up state. And now we can think of more complicated state, namely when we have some fluctuations, and in that case we would have then more of those Schmidt values which are non-zero. And this decomposition of our system is directly related to the entanglement between the left part and the right part. So the entanglement basically tells us about to which extent we can perform independent measurements in these systems, in these subsystems, and a measure or like a number basically telling us like how entangled a state is a so-called entanglement entropy. And, the entanglement entropy is the von Neumann entropy calculated for the reduced density matrix for a given subsystem. Right? So to get the reduced density matrix for the subsystem, we first write down the full density matrix for a state. Right? So we just take our state psi. For the state psi, we can write down the density matrix, which is shown here. And now we trace out the other half of the system. Like we trace out our subsystem B. And we are left with a reduced density matrix that describes all measurements on our subsystem A. And clearly, if the state has entanglement between the left part and the right part, so the measurements are not independent, then the reduced density matrix is a mixed density matrix. And the amount, or like so how mixed the reduced density matrix is actually a measure of the entanglement between the left part and the right part. And the mixedness of the state is measured by the von Neumann entropy. Good. Other questions about this? Any of those concepts that I introduced? Okay, so I assume it's all clear then. But please ask questions. I mean, like if anything is not clear, I'm happy to. But just a brief repeat. So we take our one-dimensional system, we cut it into two halves. So we have two subsystems. For these subsystems, we can perform the so-called Schmidt decomposition, which means we just expand our wave function in terms of a superposition of product states. And the concept of kind of entanglement, or like the kind of so-called entanglement entropy, is giving us a measure, basically, of the entanglement between the left part and the right part. And this is now directly related to how many of these terms we need to take into account. So if we have a simple product state, so a simple product state would be a state where we can, like as I pointed out earlier, like just we could have a simple ferromagnetic state where all spins are pointing up. Here in this simple state, we can just express it just with a single kind of Schmidt value. So in this case, the kind of so-called entanglement entropy between the left part and the right part is 0. Good. So now we can actually make some statements about some generic states, and these are quite powerful statements. So I'm now considering local and gapped Hamiltonian. So this is the only ingredient there is at the moment. Right? So we just say that we have a Hamiltonian which is local, which means that the Hamiltonian only couples sites which are nearby significantly. So this could be any kind of tight binding type Hamiltonian that we have seen before, or the Heisenberg model and the like. And now I'm saying that I want that the ground state of a system is gapped, which means we have a ground state, and above the ground state there's then some gap to the excitation continuum in a one-dimensional system. And this is all that I'm assuming. And if we just make this assumption, then we actually already know that the ground state fulfills the so-called area law. And the area law for the setup means that the entanglement entropy as function of a system size is a constant. Right? Let us now look at the following setup again as before. We take now our one-dimensional chain, as say that the chain has a length of L, and we just perform a bipartition of the chain into two half chains by cutting it into two parts, on the left part and the right part. And we ask how large is the entanglement entropy as function of a system size. And generically, if we just would have, if basically all the degrees of freedom would be entangled, then we would actually expect that the entanglement entropy would grow linearly with system size. Because in a very simple state, you could say that, well, if you have a state where, for example, every spin is kind of forming a singlet with another spin of the other side, then the entanglement that we would get is just L times log 2, right? Because every spin degree of freedom would give a log 2 to the entanglement. However, ground states of local Hamiltonians behave completely differently. So those states actually have a constant entanglement. And the way, or the cartoon picture that we can think about it, is that degrees of freedom are only nearby degrees of freedom are entangled. So for example, in the spin system, we could say that two spins that are nearby want to form a singlet. Spins that are like slightly further away still have some tendency to form singlets, but spins that are very far away, or like spatially very much separated, they will hardly sense each other. And, they don't contribute at all to the entanglement of the left part and the right part. Okay? So the main statement is that we have this kind of area law, and the entanglement entropy is independent of the length of the chain for this particular setup. So as it turns out, the states that have this property are super, super special. Right? So I was making a big point of that. The many-body Hilbert space is really big. Right? So the many-body Hilbert space, or is spanned by these d to the L basis states. But the states that have this specific property, namely the so-called area law, they are just making out just a very tiny corner in this huge Hilbert space. In fact, it's a measure zero set of states. And from this statement that I made above here, we actually know that independent of how exactly what the details are of our Hamiltonian, we know that the ground state of this Hamiltonian will be in this tiny corner of this Hilbert space. Right? So this is an extremely powerful statement. Right? So if we are, for example, looking for the best ice cream in the universe, we can probably just forget about most of the universe, but we just look in somewhere on planet Earth, likely, right? So and the same thing here. So we have this huge Hilbert space, and we can forget about most of it and just look at this this tiny corner. And this is the first good news, that this basically limits kind of the search space for our ground states significantly. So there's a question?
Is this true in some limit, the area law, or does it hold for like two sides, a chain of two sides?
Oh, the statement is that this, I mean, I have an infinitely large, well, I can have an infinitely large spin chain, or a chain. The only ingredient, the only assumptions that are made are that the Hamiltonian is local, so it just only has non-zero couplings between kind of degrees of freedom that are spatially somewhat close, and I require that there's a gap above the ground state. So these are the only assumptions that I made.
So, but it has to be a long chain. I mean, if I kind of artificially just look at a very small system, maybe it's trivial.
Oh, okay. I get your question. So if I look at the spin chain, and I have exactly the setup, and I have some length scale in the system, and this length scale will be a correlation length. And the statement that I make indeed is true for if the length of the chain is kind of larger than the correlation length. So in particular, if I look at a very small spin chain, it will actually grow up. but the moment that the spin chain is getting longer, then it will saturate. And this is exactly what this kind of cartoon picture tries to demonstrate, because here we have a length scale, like this correlation length, and we find that degrees of freedom on the order of the length scale are entangled, and the and they contribute to the entanglement entropy. But once the spin chain, or like the system that we're looking at, is longer than the characteristic length scale, namely the correlation length, then this will saturate to a constant. Yeah, thank you. Yes?
Two questions. First one, does this statement have a concrete mathematical proof?
Yes. So there is a concrete mathematical proof for one-dimensional spin chain. So this was done by Matt Hastings. But there's only a proof for the area law in one-dimensional system, as I discussed it here. Moreover, that there are many cases also in higher dimensions where the area law is found, like, for example, for some two-dimensional spin systems, but there exists no mathematical proof.
Also, is there an extension to non-local Hamiltonians?
Well, if I have non-local Hamiltonians, that there's not necessarily... Of course, the entanglement is basis dependent, so what's local in one basis can be very non-local in another basis, but for local Hamiltonians and local bipartitions, I don't think it would hold for non-local Hamiltonians, because if you lose the sense of locality, then there would be generically a volume law, namely that the entanglement entropy would grow proportionally to the length of the system. Yes?
Even if the Hamiltonians are exponentially localized?
Well, as I said, I mean, exponentially it would be a local Hamiltonian. I mean, because then they're only basically, I mean, the couplings of longer range, they are effectively zero. So. Good. Okay, so the story goes so far that we want to study these quantum many-body problems. What our problem is that the Hilbert space is so huge. So the first good news that we have now is that if we are interested in local and gapped Hamiltonians, then we actually already know that we only have to consider like a tiny part of this Hilbert space. So this is already some good news. But it still leaves us with the problem, like how can we actually represent these states, right? Just knowing where we find them doesn't help us necessarily how to write them down. Yes?
Are they always in the same, in one vicinity in the Hilbert space? Or might there be different pockets far away?
You mean like, if you, so you're asking the question if you have two area law states, if you can adiabatically connect them, or like you can connect two area law states? Is this a question?
Yes, please.
Yes, in fact, if you are on the, if you take complex numbers and you don't require any symmetries, these matrix product states are forming a convex space, so you can connect every space, everyone to everyone else. Good.
So this means that this literally means that there can be no 1D topological isolator described by MPS.
Why not?
Because you just said that they could continue on.
Oh, I said that if you do not require any symmetries.
So
So this is exactly a very good point, because we could, what I'm saying now is if you have now your space of, this is now your ginormous many-body Hilbert space, and if I just look at MPSs that have an area law, then I can actually connect, then they're forming this kind of convex set. But if I actually require certain symmetries, then not all connections are possible, so then it might be that there are some states that violate this area law. Because this is like exactly when the gap is closing. Good. So this was the first good news. So that will actually be followed by another good news, because these states that we are actually interested in, namely these area law states, they have a very nice property. And this property is now directly related to the entanglement, to the Schmidt decomposition as we discussed before. So, and for this, let me just first start off by doing some numerical experiment. And this numerical experiment is the following. So we just pick some state randomly from this many-body Hilbert space, and we perform this Schmidt decomposition that I pointed out before. Right? So we just take the state and perform a Schmidt decomposition, and now what I'm plotting here, I just sort the Schmidt values according to their size and plot them. Right? So here this is the largest one, and this is a smaller one. And in fact, this is a sufficiently large system such that I'm only plotting the 20 largest out of probably a few thousand Schmidt values that we have. And what we find here is that they're all roughly of equal size. Right? This is like a logarithmic scale, but they don't differ much. Right? And in contrast to this, if we take now an area law state, right here I take the ground state of a spin, like I take a ground state of a simple quantum spin model, we actually see a very different picture. Right here we see that the value, like the Schmidt values, decay very rapidly. In particular, taking into account only the 20 largest out of a few thousand, we actually see that they already drop to 10 to the minus 20. And that's now very nice, because we see from this, if we just take our Schmidt decomposition, where we have now a sum over a principle like an exponential number of states, right? Because the sum goes all the way up to the smaller dimension of the alpha A and alpha B. But it turns out that most of the states that we are summing over, they actually contribute a weight which is of the order of 10 to the minus 20 or smaller. So if we just don't take them to account, we actually don't throw away any information. Right? This is basically already below machine precision. So this is now the second good news. If we actually having these kind of states, these area law states, we actually know, we can, or at least we can guess from this a way how we can compress the states. Because instead of keeping all the Schmidt values, we just, all the Schmidt states, we're only keeping those that are significant in weight. Yes?
How would you physically describe these weights? You're looking at them on the computer, you're selecting somewhat set of values, but what do they mean in a physical sense?
Well, in a physical sense, these are the states that contribute to the wave function, right? So you just, I mean, the way, this is now the full many-body wave function, and we just express it in this form. And these are now, like physically, these states that contribute significantly to the wave function. I mean, one concrete
I guess my question is, what kind of measure these gives a better result than those states, or is it like more entangled state? I'm just trying to understand the physical sense.
Well, the physical sense is actually that you have a wave function. It's maybe physics is not the right way. It's just more like mathematically. I mean, it's just basically you have a.
That's what I'm trying to distinguish.
Well, I mean, mathematically, the question is kind of rather well phrased. And we just say that I give you a wave function, and you just want to basically compress it in a way by throwing away some parts, and you just basically throw away the least if you throw away the Schmidt states corresponding to the small Schmidt values. But physically, if you're thinking about some measurement, I wouldn't know how to say that you have, I don't know, you have some topological insulator and you try to measure this quantity. I don't know that there's a direct way of doing it. Good. But instead of giving a physical example, I want to give some.
Can I ask
Oh, yes.
something in this direction?
Sure.
So let's suppose that you throw away a long tail of this area law state that is very small.
Yes.
How do you know that in the complex is not representing? I mean, let's suppose that this is you throw away a lot of them. How do you know that in the complex it's not describing something that is important?
Well, I mean, I know that the integrated weight over all of them that I'm throwing away is of the order of, say, 10 to the minus 20. I can just basically, right, so if I just write down an L2 norm, like with respect, I'm just looking at how close I'm staying to the original wave function. And then I know that this is bounded by the kind of cumulative sum of those states that I've thrown away. And for this example, I can make sure that they are smaller than.
So it's something that you can always quantify, that what you are throwing away is no physical weight.
That's right, yeah. Because this is like really with respect to the L2 norm. It's, good, let me just give some visual impression of how this works. Because now, well, the argument was that, or the point was that we had this kind of coefficient matrix Cij, which expresses our state in the many-body Hilbert space. But instead of this Cij expressing a many-body wave function, those can also express an image, like the Golden Gate Bridge, for example. And then each of these numbers would basically just give the grayscale of a given pixel. And now we can play exactly the same game that I did before, like let me do performing a Schmidt decomposition of this image. So we just take the full image here, and we just perform a singular value decomposition. So we have now a unitary times a diagonal times another unitary. And now what we can do is we can sort the singular values, which are equivalent to the Schmidt values according to their size, and only take into account the dominant Schmidt values here, and from those reconstruct the image. Right? So this is exactly what I did before for quantum states, but now we can do it here for this image. Yes?
Now you also somehow split up the image into...
Well, now I'm having previously I said that, okay, the IA, they are describing the degrees of freedom on the left, and J is describing the degrees of freedom on the right. But for the image, this I is maybe the y coordinate, and the j is the x coordinate. And then we can just reconstruct the image from a few Schmidt states. So we have here an image of where the smaller dimension is maybe 1,200 pixels. And now if we just take 4 out of these 1,200 states, we just see some very kind of blurry picture. But as we take more, like with 16 already it's recognizable that this is probably a bridge. And with 64, which is just 1/20th of the full dimension, we actually already see that most of the features are represented. And then we can successively add more states, and then more and more details are added. But we can see already in this kind of example, just taking into account a few of those many singular values, we already kind of can recognize most of the features in this image. And this is sort of the idea of this kind of compression scheme that I just suggested for quantum states. Well, a fun fact is that you can now look at which of the artists has the least information in his images. And there's some paintings by Mondrian, which if you just not would have these colorful boxes, that would be actually states that have no entanglement, or that can be represented just exactly with a singular, with one singular value. So this would be a close representation of a product state of a quantum system. Good. So now, yes.
Okay. We need to compress the image more or less to know what is the reality.
Mm-hmm.
Here we want to compress something that we don't know.
Yes.
So how do we know that we are doing a good job?
Oh, as I pointed out, I mean, there are now different schemes that we can follow. And the one that I'm going to go to now, you could say that for some reason you happen to have the full wave function. Now you can perform this this Schmidt decomposition. Then you just would have all the Schmidt values. And then you could just say that, okay, you just truncate the, so you just would perform this Schmidt decomposition. And you have now the Schmidt values that decay very rapidly. There shouldn't be smaller than 0. And then you can say that, well, if you now just truncate this part and you know that the sum over alpha from, I don't know, alpha larger than some chi is of lambda alpha squared. If this is smaller than a certain threshold, then you know that this is kind of the accuracy of your truncation. So you know that if this number here is smaller than some epsilon, then you know that your wave function is represented in this precision. And now I actually want to just turn these ideas or these insights into some sort of practical idea. And now the idea is exactly what I said before. We actually now assume that our wave function is, so we just know our wave function exactly. And the wave function that we know exactly, we just know it in terms of having access to all the amplitudes in our many-body wave function. And now, slowly, I will start to introduce some sort of graphical notation for the tensors. And this is pretty quite easy. So we just say that we have now our many-body wave function, and this is now this gray box here. And this wave function has now is actually a rank L tensor, so which means we have for an order L tensor, which means we have like L legs, right? So for a system of 5 sides, we have now 5 legs, and each of these legs that's sticking out of this box corresponds to a given kind of physical index. Right? And again, this is an object that we really don't like to store because the size of this or the elements of this rank L tensor is increasing exponentially with L. So now, just using these insights that we had before, we can actually now come up with a compression scheme. Right? So this compression scheme would be extremely useful if you have, for example, a friend who has like a really big computer that can do your calculation, can find the ground state of your local Hamiltonian, but then he wants to store it on a USB stick to hand it to you. And for this kind of scheme would be very useful. And the idea is now the following. So here we now take the amplitude of our many-body wave function. So this is now a d to the power of L dimensional huge object. Now we start with the first side. For the first side, we perform a Schmidt decomposition, exactly the way that we've done it already a couple of times. So we just expand it in terms of the bases on the left and on the right, and perform then a singular value decomposition. Now we can actually write down our many-body wave function as a sum of some kind of unitary here on the left, the Schmidt values, and then some other unitary on the right. But you see that the part that's left on the right has left, like we just lost one leg, which is now contained here in this structure. But this is now a procedure that we can perform successively. Right? So after having done this here, leaving us now with a 4-legged object, we can now perform a singular value decomposition of this 4-legged object. And now we just have another kind of tensor here that relates the left part to the right part, and we are left with a 3-leg, and then we can successively cut it such that eventually we actually express our rank L tensor that we have here in terms of a product of these rank 3 or order 3 tensors. And at each step, we can actually perform, at each step, we would find that if we do this exactly, we would find at each step the bond dimension or the number of states that we need to take into account is growing exponentially. However, at each step, we can actually then just toss away those that have only a very small Schmidt weight and then move on. And by this, we're actually then achieving this kind of compression, namely that we start from an object where we have to store d to the L elements, and eventually we're actually ending up with an object where we just have then L objects that only have kind of chi-squared times d complex numbers. Yes?
So A is the unitary in the SVT, right?
Yes, right. So here it becomes apparent. So we just have our wave function. We perform an SVD of the wave function, and this A here, this is actually the unitary part of this. Okay. So, and again, this by itself is not a super practical scheme because it actually assumes that some of your friends is capable to find the exact wave function and then you compress it. I just, instead of proposing this as a concrete idea for getting your states. I just want to use this as a motivation for having this kind of class of states as something useful, right? Because now, if we just believe in this, and I think we have we do have a good reason for believing it because of the proofs or the mathematical proofs that exist for the area law, we actually have now a way to compress our d to the power of L dimensional object into L times d times chi squared. And chi squared, this is now the number of Schmidt values, or the number of Schmidt states that we keep at each step. Right. So what we have achieved so far is that we can express our many-body wave function in terms of a product of these matrices. Right, and again, in this notation, each of those objects here is a tensor that has now a certain number of legs sticking out. And if I just connect two adjacent tensors here, this means that I'm just summing over those indices. And the great thing is that if we actually have this kind of representation of a state, then we can calculate basically everything that we are interested in. Right? So the norm and all kinds of expectation values, correlation functions, and so on. Good. So just to summarize briefly our achievement, so for a certain class of Hamiltonians that we are interested in, we actually know that the ground state has very special properties that allows us exactly where to look. And for this kind of class of states, we actually know how to express them efficiently. By efficiently, I mean that we can express them with some numbers that, like with some information that doesn't grow exponentially with the system size. And what I want to do now is I want to actually just show to you some ideas how we can perform calculations with these class of states. And moreover, I want to discuss how, starting from some microscopic Hamiltonian, you can actually find an approximation of the ground state in terms of these states. And for this, I want to give you some discuss some nice properties of these states. So, of course, for a general state, all of these matrices can be different, and so we have all these indices. But from now on, let us assume that the system is translation invariant, so we don't have to worry about these indices so much. It's just making it a bit easier to think about them. So let us now think of a state which in principle is infinitely, like for an infinite system, and we have the same matrix just repeating over and over again. One thing that we notice when we write down states like this, right? Because this is now the product of many, many matrices, thus matrix product states, we actually find that this is not a unique state. You can in particular assume that we have some matrix product state given by some matrices A on each side, and now we say that, well, we just choose some different set of matrices where we just take any invertible matrix X, multiply it to the left and the inverse to the right. Then we see that after multiplying all these matrices together, then it's representing exactly the same state because all these matrices X cancel. Right? So basically, what I'm saying is that for a given state, there exist many, many different matrix product state representations. And this actually allows us that we can use this degree of freedom to pick a particularly convenient form of a matrix product state. Convenient means that we have a form that will be very useful for calculations that we want to perform. And the particular form that we want to choose is a so-called canonical form. And for this, we choose it in such a way, we choose the matrices in such a way that we directly relate the Schmidt values, the indices, to a Schmidt decomposition as we did before, right? Recall for yet another time, the Schmidt decomposition we just kind of perform for like any kind of bipartition, where we just have states describing everything to the left, describing everything to the right, with some Schmidt values. And these are orthogonal states. And now we're actually choosing to express our wave function in exactly this form. So we have here now the amplitudes of our many-body wave function, and we are now writing down a form where we express our matrices A as a product of some diagonal matrix. So the diagonal matrix we put on the bonds, and this is just the diagonal matrix containing all the Schmidt values that we get here from the Schmidt decomposition. And we have these matrices or rank or order 3 tensors gamma that relate the local basis and the Schmidt basis. Right? So then we have this particular form. And to be a bit more specific, the matrices gamma and lambda, well, the lambda matrices are simply just the diagonal matrices containing the Schmidt values. And the gamma matrices are chosen in such a way that if I say I take my matrix product state and I just contract everything on the left of this matrix product state, then I'm getting the left Schmidt values, the left Schmidt vectors. And if I contract everything right of a given bond, I will get the right Schmidt vectors or Schmidt states. Right. So, and if I choose the this particular canonical form, then because of the orthogonality of those Schmidt states, I actually have this identity. So, particularly if I'm multiplying all the matrices left of this, keeping this index fixed to some value alpha, then I have the Schmidt states alpha. If I keep another index alpha prime fixed here, multiply all matrices to the right, then I get a Schmidt state alpha prime. And if I just overlap them, they should be orthogonal, so this will be a delta function. Good. And having this kind of specific form, I mean, because of the orthogonality conditions, we can now very easily calculate all sorts of expectation values for those matrix product states. So, for example, we can just calculate local expectation values, and we can calculate correlation functions. Now that I'm showing this, I realize maybe this kind of graphical notation needs a little bit of more explanation. So let me maybe say a few words about this, because this will be quite useful. So now we have these kind of graphical representation of our tensors, right? Specifically, we say that if we have like a matrix Aij, this would correspond to just some object where we have just two legs sticking out, right? So one leg would be the leg I, the other one would be the leg J. If we just have a matrix product, it would be, for example, the sum over Aij, Bj, K, and this would be a matrix Cik. If I just want to express exactly the same ideas in terms of the this kind of symbolic representation, I just take my two matrices A and B, and this index J that I want to sum over, I just connect them, right? So this would be now our object C, right? So I guess that's understandable. So now we can wonder, like, how. Let us now say that we have now our wave function. So the wave function, as I pointed out, describing our one-dimensional system, say, is now like a matrix being an order or rank 2 tensor is now a rank L tensor. So we have now L legs sticking out of our object. Good. So now I can, if I want to, if I have a given many-body wave function, right? So the many-body wave function is then given as the sum over I1 through IL of our psi1 through IL of I1 to IL. This is now our many-body wave function that we are interested in. So now let's say that for this many-body wave function, we want to calculate some expectation value. Right? Let's say that we have a spin system, and we want to calculate the local magnetization on a given site I for this wave function. Right? So what this means is now basically that we have now the sum over I1 through IL, and then I1, say prime, through IL prime, and then we have psi I1 through. Oh, let me first maybe just calculate the norm, which is even easier. Let me say, if we just calculate the norm, then this is just the sum over all those guys times the sum over as a prime IL prime times, because these are orthogonal sets, then we have just the delta function IL I1 IL prime. Now you see that this is like quite of a lengthy expression to write down, but I can now write down exactly the same expression just using this graphical notation. And in this form, this is just this. We have now our psi, which has a number of legs sticking out, and our psi conjugate, and we just kind of multiplying each leg with the other leg, so because of this delta function. Right? So now you see maybe the beauty or the of this kind of graphical representation. And now if you want to calculate expectation values, as I say that we just calculate expectation value of some sigma z operator or SZ operator on a given site. Now this corresponds to something like this, but on one leg we apply the SZ operator, right? So this would be now the expectation value of an SZ operator for a given site. And using the idea of matrix product states, we say that, well, what we do, we actually expand our many-body wave function into this product of these individual matrices. And when calculating the expectation value, we just have shapes like this. Oops. And now the simplification, and this is why I was so excited about this canonical form, is because what if we want to do this kind of, want to calculate these expectation values exactly, we actually have to multiply all the matrices. Except that when we have these orthogonality relations, namely that if these guys here all give delta functions, then we know that whenever we multiply something from the right to here, we find that this is a delta function, this is a delta function, so we can actually remove all those guys, and we just keep our lambda squared here. We can do the same from the left, and we keep just the lambda squared here, and we can, by this, just calculate all sorts of expectation values just quite locally, and the same is true for the these correlation functions. Yes?
You use to close on the boundary is the orthogonality of the Schmidt vector?
So I'm using exactly the fact that if I just multiply these matrices, that they will right, that the Schmidt states are orthogonal, and then I can just always move it from the right to the left and from left to right. Okay.
Sorry, is lambda here? Do you claim it to be the matrix, the SVD diagonal matrix?
Yes.
So each lambda is the list of eigenvalues of SVD from the left to the right.
Yes, that's right. Yes, and I mean, assuming I mean, this is like why this is like like this kind of beautiful form. Let's say that we have a matrix product state given here, where we have now gamma, lambda, gamma, lambda, gamma, lambda, gamma, lambda, gamma, lambda. And now if you just wipe this out here, then this is exactly the Schmidt decomposition at this given bond. Right? So now these ones here are the Schmidt states alpha left. This is lambda alpha, and this is now alpha to the right. I mean, before starting now about algorithms, maybe take a 5-minute break, and then also people can come to ask questions if you like.